Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel, and it also helps us reach others in need of assistance with these topics. So in today's video, we're going to be covering statics, and we're going to be looking at 3D components and resultants, and this will be the second problem in this particular series. So what we have going on here is that we have this picture shown here, and the description states that the screw eye is subjected to two forces of F1 and F2 as shown. We need to express each of these forces in Cartesian vector form and then determine the resultant force in Cartesian vector form from these two forces being combined together. Then we have to find the magnitude and the coordinate direction angles of that resultant force. So all Cartesian vector form is that we're going to get a force, and we're going to have the x component of that force, then we're going to have the y component of that force, and we'll have the component in the z direction of that force along each axis direction. Now, when you're looking at these 3D problems, you have to make sure that you're looking at the correct axis direction, because not all the time is the x here, the y here, and the z is here. Sometimes the y is vertical, z is here, and then, or x is here along the y, and then z is down here. It just depends upon what the problem is showing, the coordinate direction angle. So you have to make sure you're using the correct one. All right, so let's start with F1 up here, and we're going to express it like this. Now, there's multiple different ways that 3D forces can be expressed with their locations. F1 is being expressed in the most difficult format, I guess, is called transverse and azimuth angles. So what this means is that we only have two angles showing where F1 is located. Right now we have a 60 degrees right here, and we have a 45 degrees right there. And the 45 is to this darkened line right here. And all this is showing is that if I had some kind of, let's say, light up here, we'll just draw a sun. This projection line is the shadow or the projection of F1 along the XY plane. And that's what the 45 degrees is measuring. So you know you're dealing with transverse and azimuth angles when you only have two angles, plus one of the angles is being measured to a projection line directly below or next to your force you're looking at. So with this transverse and azimuth, when we look at F1, we're going to have two angles, and I'm going to represent them as theta and phi. So theta will be your horizontal angle measuring to your projection line or your projection force. So in this case, theta will be that 45 degrees from the y-axis. Now, you have to be careful because there's multiple different ways that you can do this as well. And it just depends upon how or what you feel most comfortable doing, or how your professor dictates that you do it, because sometimes some professors will dictate how you do it. In my classroom, I don't care, because in real life, there's multiple ways to get to the same answer. So what I'm saying is that we can just make this theta right here and understand that that theta is from the y-axis to the projection line. Sometimes people will say, well, you have to have theta go all the way from the positive x to the projection line. That's fine. That's just another way to do it. So we are using theta as 45 off of the y. Now, the phi will be from your positive z-axis, or the positive vertical axis, which is RZ. So this would be my phi angle right here. Well, this phi angle will just be 90 degrees minus off the 60 degrees, because the 60 degrees will go to your projection line, which is your plane in between your x and y. That's your flat surface. So the 60 degrees is telling you how much you are inclined off the flat surface there. So phi will just be 90 degrees minus off 60 degrees, which gives you 30 degrees from the positive x, or positive z, sorry, which I'm just going to write as plus z. All right. So now, how do we find our x component, y component, and z component for F1 utilizing this information? So let's start with the easy one first, which is Fz. Fz will be right here along the z-axis. It will be pointed upward because our Fy force is pointed upward towards the positive z-axis. And we're taking upward as positive along the z here. So we will have our force of F1 And then we're going to use cosine of our phi angle because the phi angle is adjacent to the z-axis. So we're going to use cosine whenever we are adjacent here. So plugging in our values here, we would have 300 newtons, cosine of phi, which is 30 degrees. And that gives us an FZ component of 259.8 newtons in that upward z direction. Now, how did I know that it was cosine and sine? Well, you can look back at the 2D component and resultant videos that we have here. We go into great detail why we use sine and cosine. It's the same methodology here, just now in 3D. All right, so let's move on to the harder ones, which is x and y. So let's start with fx, and this means that we will have this projection force along the x-axis here. Now, F1 is pointed in such a way that if this x-axis were to continue right here, it would be pointed in the negative x-axis because we are taking this as the positive direction. Typically, you take the positive direction where the actual label is. So Fx will be our main force, no matter what direction you're looking at. It will always be your main force that you're breaking up into its components. So we'll be looking at F1. And now what we have to do is that we have to project this F1 force down. We have to project it down into the plane, into that projection line. So this is like looking at it in 2D, such like this, where this is F1, this is the Z, and this is the XY plane. So we have this angle of phi here. So we would just be F1 sine of phi to get it down to the projection line, or you could have used cosine of 60, it's fine. And then once we have it in the projection line, what we have going on is that you can look at it like this, where this is the negative x, this is the y, this is my projection line, which is now F1 sine of phi. And what I have here is theta of 45 degrees. So I have dropped it down to my projection line, and then I have to then project it, or not project it, but then move it to my x-axis here. So you do this one first to get it to the xy plane. And then you do this again over here with the negative x and y to move it to the x-axis. So we'll have F1 sine of phi, and then from this diagram, well, then what will it be? It will be the sine of theta. And once again, it's the sine because, well, I want to project it to the xy. Xy is opposite my angle of phi, so it's sine. Anytime you use opposite, it's sine. And then over here, if I need to get it to the x-axis, well, I'm going to use its opposite, my theta, so I'm going to use sine, which is my opposite trigonometry value here. So plugging in everything here, I know it's going to be a minus value because I am in the negative x direction. So it'd be minus 300 newtons sine of phi, which is 30 degrees. And then it'd be times the cosine of theta, which theta is 45 degrees. And this gives me a minus 106.1 newtons. Now, this is where I said before that some people will take it from the positive x. So if you take it from the positive x direction for theta, that would just be 90 degrees plus 45 degrees. You'd have 135 degrees. And you would then use that as your theta angle in here. Oh, I'm sorry. I have a mistake right here. This is not cosine, it is sine of 45 degrees. Sorry about that. So you would use 135 here, and then it would automatically pop out the negative symbol. So you have to be careful when using what angles you're actually measuring from and where your location of that component's actually pointed towards. So you have to watch out because this is where I said there's multiple different ways that you can do it and arrive at the same answer. So you have to be careful of that. All right, lastly, let's get our Fy. And Fy, once again, will be F1 projected down to the xy, which will be sine of phi. And now I have to project it over to the y, which will be cosine of theta because the angle is measuring from that angle or from that coordinate direction. And it's adjacent to it, so it will be cosine, which is the adjacent. And this will just be 300 sine of 30 degrees. This time cosine of 45, which the sine and cosine of 45 is the same thing, which this now pops out to be 106.1 newtons. And is that going to be positive or negative? Well, if we go back up to Fy right here, well, this is pointed in this general direction, and that will be pointed in my positive y direction. Over here would be my negative y, and it's not pointed over there. So it'd be a positive y. So that's why I have a positive 106. All right, so to complete the first portion, which says the Cartesian vector for each force, well, if we were to plug in the Cartesian vector for F1, it would look like this. So it'd be F1 is equal to my Fx, which is minus 106.1 newtons, I hat, plus Fy, which is 106.1 newtons j hat, and then plus my Fz, which is 259.8 newtons, and that'd be my k hat direction then. And that'd be my Cartesian vector for F1. All right, so now we're going to repeat the process, but we're going to look at F2. So what I'm going to do here is that I am just going to restart here and erase all this information because I really don't need this anymore. Because what I've done is I've taken F1 and I have split it into its individual x, y, and z components and express them in Cartesian vectors. So now I have that. And that's eventually what I'm going to utilize here in order to get my resultant as well. So I can erase all this now because I've simplified everything down into that Cartesian vector form shown right below here. So looking at F2, F2 is going to be different than F1 because it's actually much easier because I actually have 3 angles showing where my F2 is located. And I have an angle from each axis here. So it makes it much, much easier to utilize here. So utilizing F2, I have 60 degrees off the x, 45 off the y, and then a total of 120 off of the z here. So what this means is that my F2 will be in the positive x direction, the positive y direction, and the negative z direction because the z is larger than 90 degrees from the positive, which means it's pointed in the downward direction. So whenever you have 3 angles like this, you can use the directional cosines in order to solve, which is much easier and less confusing to do here. So using directional cosines, it's essentially just going to be Fx is equal to your actual force of F2, cosine of the angle off of the x. Fy will be equal to basically the same equation here, F2 cosine of the angle off of the y, and then Fz will be equal to F2 cosine theta z, which is the angle off the x. And these are all going to be the angles off the positive coordinate axis directions. So plugging in here, we have F2, which is 500 newtons. This will be cosine of theta of x, which is 60 degrees. And this gives me exactly 250 newtons positive x direction. And then we just simply just exchange the angles here for each one because the F2 force is going to remain the same. 500 cosine of 45, this 45 off of the y. And that gives me 353.5 newtons. And then lastly for FC, 500 newtons cosine of 120 degrees. And we expect this one to come out negative because the angle is larger than 90. So that means Z is pointed downward. And it does. It comes out to be a minus 250 newtons because the negative comes in here from this cosine of 120. So you see how much easier that was when you have all your directional cosines? So expressing F2 in Cartesian vector form, well, we would have the X, which is 250 newtons, I hat, plus the Fy, which is 353.5 newtons, j hat, and then minus off the Z, which is 250 newtons with our k hat here. And that would be how we would express each force in Cartesian vector form. So then that takes care of the first part. Second part says determine the resultant force in Cartesian vector form. Well, how do we do that? Well, the resultant force in Cartesian vector form will be equal to this, where it's the summation of my total x's plus the summation of my total y's plus the summation of my total z's. Oh, not j, that's k. Excuse me. So all we have to do is sum up the total x's, sum up the y's, and sum up the z's for each force. So thankfully here we only have 2 forces. So the summation of my x's is just going to be 250 newtons minus 106.1 newtons. And that gives us 143.9 newtons in the x direction. And you essentially just repeat that process for each portion here. So for the y, we have 353.5 newtons plus 106.1 newtons. And that gives us 459.6 newtons. All right, and then lastly, repeat that process for FC. And now we have minus 250 newtons plus 259.8 newtons, and that gives us 9.8 newtons in that z direction for our resultant force. So our resultant expressed in Cartesian vector form will just be these guys right here in each direction with I, j, k. So we would have 143.9 newtons, and that'd be our I hat, plus 459.6 newtons, and that would be our j hat, and then plus 9.8 newtons, and that would be our k hat. And that would be our answer for the resultant force in Cartesian vector form. All right, so we are just getting our answers here left and right. So we have done this one as well. And now, lastly, we have to find the magnitude and coordinate direction angles of the resultant force. So what this is saying is that we have it in Cartesian vector form, which gives us how much the resultant is in each direction, x, y, and z. But now we have to find a single resultant magnitude value, and then we would have to locate it off of the x, y, and z with our coordinate direction angles. So this is going to be very similar to the process that you use for 2D. So the magnitude of my resultant, which I'm just going to call mag r, or you can call it r sub mag for a resultant, and I'm sure there is an actual expression that you can use for vector notation here, but it doesn't matter. It all means the same thing in the end. So this will just be the summation of your x's squared plus the summation of your y's squared plus the summation of your z components squared, and then all of that will be square rooted. So basically just take your Cartesian vector forms, square each one, add them together, and then square root it. And that would be your overall magnitude. So what I would have is 143.9 squared, plus my y, which is 459.6 squared, plus my z, which is 9.8 squared. And then you square root all that, trying to make a straight line there. And this pops out to be a total magnitude of 481.7 newtons. And that would be how much my resultant force actually is in a single force vector. Well, that answers part of it. Now we have to answer, well, what's the location of this thing from the x, y, and z axis? Well, this is going to be kind of like the inverse relationship of what we did with F2 up here, where we are looking now for these angles off the x, y, and z. We have the magnitudes. Well, we have the overall magnitude. Now we just have to find out what's going on here because we can use the components of x, y, and z for our r. So instead of F2 here, imagine that we are looking at r. So typically, now this is not always the case, but typically what we do is that we say alpha is off of the x axis, and then we say beta is off of the y-axis, and then we say gamma is equal to the angle off the z-axis when we're looking at our final resultant. Instead of using theta x, theta y, and theta z, which typically has to do with the component forms, alpha, beta, and gamma have to do with the resultant magnitude in the end. Now, that's not always the case, but that's just typically what's done. All right, so working through our equations here, as I said, rearranging what we did for F2, alpha will just be the cosine inverse of the fx component over r for our resultant, and this is only dealing with the resultants. So we would have cosine inverse of fx, which is just our total summations of fx, which is 143.9 over our magnitude of 481.7. And this gives us a total of 72.62 degrees off of the x-axis. All right, well, repeat that process for the y. And the only thing you're exchanging here is fy for fx. Everything else is going to be exactly the same type of calculation here. So it'd be cosine inverse of 459.6 over 481.7 newtons. And this gives us 17.4 degrees. And lastly, we only have one more angle to do here, which is off of the z-axis. So it'd be gamma is equal to cosine inverse of Fz over our resultant magnitude. So plugging in actual values here, we would have cosine inverse of 9.8 over 481.7 newtons. And this gives us a value of 88.8 degrees. And these would be your directional cosines or your location angles for your resultant magnitude. And that's how you would answer this entire problem. Now, you actually wanted to see a picture here. This is what it would look like with those angles. So we would have our resultant magnitude in a single vector form of 481.9. And here's our angle of alpha of 72.6. Here's our angle beta of 17.5. And here's our angle gamma right here off the z of 88.8 degrees. And that is where our resultant force would lie. And that's how you would answer that entire problem. So I hope this video is helpful. And if you want to see more problem solved this Friday, please check out the other videos on our channel. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel because all of that does help us out greatly. Thank you for watching, and I hope you have a fantastic day.